everyone. Welcome. My name is Miriam, and I'll be hosting today's session on behalf of Ceres Greenhouse Solutions. Today's topic is Before You Break Ground, Greenhouse Simulation with Real Climate Data. Designing a large-scale greenhouse involves a high degree of interconnected complexity. Glazing, thermal loads, HVAC, humidity, and crop outcomes are all linked. When those decisions are based on static calculations and general assumptions, the gap between expected and actual performance can be significant and costly to address after construction. In this session, we'll walk through the building performance simulation process Ceres uses on commercial and research greenhouse projects and some residential, demonstrating live how site-specific climate data, thermal modeling, CFD airflow analysis, and HVAC simulation work together to inform design decisions before construction begins. Please drop any questions into the Q&A as they come up. We'll address them during the live Q&A at the end. We do ask that questions stay relevant to today's topic. This session is being recorded. The replay will be available in a follow-up email on our YouTube channel and on our website. I'm pleased to introduce our guest for today, Robert Fisher, Head of Engineering at Ceres Greenhouse Solutions. Robert leads greenhouse design and simulation using advanced modeling, airflow analysis, and HVAC engineering. With more than 2 decades of experience, he helps commercial growers and research teams reduce project risk through data-driven design decisions. Before we hand it over to Robert, just a quick disclaimer. The information provided during this webinar is for general informational purposes only and is based on the expertise and knowledge of our greenhouse specialists. The advice and recommendations provided are intended to assist attendees in understanding various greenhouse systems. Participants are encouraged to consult with a qualified professional or conduct further research to address any specific concerns or requirements they may have. The hosts and organizers of this webinar are not responsible for any actions taken based on the information presented. Okay, over to you, Robert.
Pull my screen up here. And am I sharing the screen at this point in time?
It is loading. And there you go. What's that?
Greenhouse design rarely fails due to the team's lack of experience. It fails when important assumptions are never tested together. Rules of thumb, design day calculations are useful, but they usually represent a one moment in time. In reality, the weather, the solar gain, the crop transpiration, and all of the equipment in your structure are constantly interacting together. Dynamic simulation allows us to test those interactions early before assumptions become costly design or operational problems. When design assumptions miss the real operating conditions, the consequences extend well beyond the equipment itself. Oversized systems can increase capital cost, short cycle, and operate ineffectively, while undersized systems may fail to maintain the temperature or the actual humidity targets during critical periods. Poor airflow, moisture control, or systems integration can create uneven crop conditions, condensation, disease risk, and actual production instability. These are not simply engineering inconveniences. They affect crop quality, the operating cost, the reliability, and the facility's ability to perform as intended. A greenhouse should be understood as one connected environmental system rather than a collection of independent components. Changing the glazing affects the solar gain, heat loss, surface temperature, condensation risk, and the equipment sizing. Adding shade may reduce cooling demand, but it also reduces the available crop light. Increasing ventilation or fogging may relieve daytime overheating, but create additional demands that are not easily understood at that moment in time. The important point is that improving one variable can unintentionally make another variable worse. That is why design decisions need to be evaluated together as part of a full greenhouse system. Simulation changes the discussion from what happened to what normally happens if we use this equipment to how this greenhouse is actually expected to behave under the site-specific climate and operating conditions. It lets us evaluate performance hour by hour, identify when targets are exceeded, determine how long those exceedance last, and understand what is driving them. It also lets us compare the glazing, the shading, the ventilation set points, the controls, and all of the equipment strategies before the construction actually begins. Simulation does not eliminate uncertainty, but it'll give the project team a structured way to identify it, test it, and make better decisions before it becomes a construction or operational problem. IESVE is a digital test environment that Ceres uses to evaluate greenhouse performance before construction. It allows us to test the greenhouse as a complete system rather than just reviewing the envelope and equipment separately. The value is not simply producing data, it's actually understanding how the greenhouse is expected to behave, why performance problems may occur, and what design decisions can actually reduce before we are committed to buying all of this and making it happen. So IESVE is a professional building performance simulation platform. It's used by architects and engineers across the building industry for thermal, energy, HVAC, daylight, and airflow analysis. It combines a three-dimensional building model with weather data, all of the material properties, the internal loads, the operating schedules, and the system controls. Ceres adapts these capabilities to greenhouse projects by representing the transparent envelope, the crop-related moisture and heat, all of the lighting, the ventilation, and environmental systems that are incorporated. A simplified sizing tool will typically estimate just a peak moment in time for the cooling requirement, and that is useful for an early screening, but the dynamic simulation answers a broader set of questions. It'll show when those peak hours are actually occurring, why it's occurring, and how often the systems operate at that condition, and how temperature and humidity behave throughout the rest of that year. It can separate the sensible and the latent loads. You can evaluate condensation risks, quantify the exceedance hours over set points, compare operating and control strategies, and support detailed airflow analysis through CFD. The distinction is between calculating a number and understanding a system that actually produced that number. Ceres does not begin by just opening up the software and drawing a greenhouse. We begin by understanding what the owner is trying to accomplish, what plants and occupants require, how the facility will operate, and what level of risk the project team considers acceptable. Then we assess the climate, establish measurable design criteria, validate the envelope and system inputs, and build the model around those requirements. The model is therefore a representation of a specific project and operating concept, not a generic greenhouse template to be used in other locations. The final step is to translate the results into decisions about the envelope, the mechanical systems, the controls, and the operation. Before evaluating the performance, we need to define what success performance means. We consult on many different types of projects, such as commercial crop facilities, botanical gardens, research greenhouses, conservatories, and even event spaces, all of which utilize greenhouse construction. But their performance requirements can be very different. We document the project use, crop and occupancy needs, the strategy for operating it, and all the key constraints, including budget, utilities, redundancy requirements, expansion plans, and the risk tolerance. This will actually generate our owner's project requirement, which is the OPR, that's used to actually judge and hit these performance targets. That's what we're chasing, is what the owner actually needs and wants to be successful. The climate should influence the greenhouse concept from the very beginning, rather than be added in at the end. Temperature and humidity patterns, solar radiation, crop light availability, wind, natural ventilation potential, and extreme events. This helps determine whether the proposed operating season environmental targets are realistic for the selected location. It also helps the team decide whether the naturally ventilated, semi-closed hybrid system or more of a mechanically controlled system is appropriate. These decisions need to be made early before the envelope, equipment, and control approach is actually locked in. The owner's requirements are then converted into measurable criteria before they can be modeled, tested, or verified. Statements such as maintain good growing conditions or become temperature ranges, humidity limits, high temperature targets, airflow requirements, all of the things and expectations that is required, we kind of bake into what is a good growing condition, because that's not measurable. We also define the system capacity. Do they need redundancy? How much energy will be used? The operating cost? And is there any future expansion and flexibility priorities that the owner needs? This translation step creates a clear technical basis for evaluating whether the weather and the design of capable of delivering what this owner actually expects. The greenhouse envelope influences nearly every major simulation result. If it's glass, polycarbonate, acrylic, ETFE, do they have insulated walls, shading systems, thermal curtains? All of this creates different behaviors. Each assembly has its own thermal characteristics, and those properties affect the crop light, the heating demand, the cooling demand, all the condensation, humidity risks, and also the energy use. So at this stage, we identify the proposed envelope, the assemblies, and determine which physical properties must be represented accurately in the model. That ensures that the later system analysis is built upon a reliable foundation. Public data does not always describe the performance of the complete installed assembly. A panel may have a very strong center of pain value, while the frames, joints, and edges leak a lot of air or will reduce overall performance. Ceres reviews the manufacturing data, project documents, and any specialty material information. We use a lot of special materials and experimental films at request. So we utilize software such as Therm and Window that are developed by LB&L Berkeley Labs whenever appropriate to understand these material properties before we put them into the energy modeling software. When values still remain uncertain, we'll document the assumptions and test how sensitive they are. If the envelope inputs are wrong, the heating, the cooling, condensation, everything else will be wrong. So one of the most important things is making sure you understand the properties and the elements that you're actually putting into the building. Once the project requirements and envelope properties are understood, we bring it all together in a coordinated analysis model. The model connects the proposed building with site-specific weather, the crop-related loads, internal equipment, schedules, environmental systems, and controls. It's not just an architectural model imported into another program, it's an engineering representation of how the project is expected to be constructed, occupied, operated, and actually controlled in the future. That allows meaningful performance questions to be tested, and then the results are used to support good design decisions. Geometric foundation that we use is typically created in Revit at our location. For Ceres, we have standalone greenhouses that are standard. We've created parametric components to allow us to configure these kind of quickly and efficiently. For customer third-party designs, we'll review and coordinate with the architects or consultants on the geometry. If necessary, we'll pull those in ourselves, make those and pull them back in. But before export, all of the enclosed spaces and major openings are confirmed and validated. After BIM, the geometry is coordinated, the relevant elements are transferred into IESVE and reviewed carefully. We confirm the scale, the orientation, the dimensions, all of the walls, roofs, everything that has been put in there, we need to validate that it actually transferred over correctly. We then establish the thermal spaces, the environmental zones, and repair or simplify the geometry that could actually produce unreliable calculations. Importing the model is basically the starting point. The real work is converting the geometry into an analysis-ready model that represents the greenhouse's environmental behavior. Geometry defines the shape of the greenhouse, but the physical properties and the climate inputs determine how that shape performs. We assign validated constructions, solar and visible light transmission, surface properties, thermal curtains, shading elements, infiltration, operable assumptions, site orientation, and the site-specific weather. Each input should reflect the actual project whenever that information is available. An empty greenhouse model does not represent how a greenhouse functions. We need to account for crop type, growth stage, transpiration, lighting, equipment, occupants, irrigation-related moisture, day and night set points, seasonal schedules, event shutdowns, any kind of setback modes that are programmed. These internal conditions can create large, sensible, and latent loads. And in many facilities, the solar load and the crop transpiration that creates the moisture load are as important, if not more important, than the outdoor weather. Accurately representing when and how these loads occur is essential to predicting the heating, the cooling, the ventilation, and the moisture control performance. Equipment capacity alone does not determine whether the greenhouse will perform successfully. We need to represent how that equipment will be coordinated. We have heating, we have cooling, there's dehumidification, there's ventilation, circulation, air distribution systems are all sequenced and staged and controlled in IESVE. We then take those set points and things in the future and we'll morph those over towards the actual control systems that we use. But this particular model includes all of the operating sequences and set points, any kind of modulation ranges and recoveries. This allows us to use this system to cooperate or conflict. Does a system work together? Is this component fighting this component? Things of that nature. A correctly sized coil can still perform poorly if the airflow and humidity logic is not accurate. A simulation is not trusted just because it ran without an error. Before we use the results, we actually review the inputs again for accuracy. We distinguish the project-specific information from any temporary assumptions that were made. And then we compare the model behavior with measured facility data whenever this type of information would maybe be available. We also check whether the model behaves logically. Do the loads actually occur when we expect them to occur? Do the controls respond in the correct direction? Do the results change reasonably when an input's entered? Validation combines technical review with engineering judgment and comparison against any available evidence we have. And only then do we believe the model is ready to support some of our design decisions. In a moment, we're going to do a live demonstration to compare two buildings with the same overall dimensions. We're going to look at a 30 by 100 foot greenhouse with an ETFE envelope, that is a clear film, against a 30 by 100 foot insulated metal panel building. Both are exposed to the same climate conditions, which allows us to see how that enclosed property changes with the building's response. For each output, we're going to review what was, we evaluated, what the results show, and what it means for a project. The goal is not to teach every step of the software. The goal is to show how the model helps us understand building behavior, identify risk, and make better decisions during design. We will use Vista Pro, which is the built-in analysis tool of IESVE, comparing the thermal response of the buildings. We will then compare the sensible latent light loads. This is the most important takeaway on this will be the solar gain versus the light loads we'll take a peek at. We're also going to show how we compare the interior surface temperature for dew point and humidity concerns. There's two different directions we look at there. And then after the IESVE demonstration, we'll review some CFD examples from some previous projects that was prepared by Sean Haley and Tyler Zimmerman from our engineering team. And that will demonstrate the different types of airflow information and analysis that can be provided. We use CFD to see how the air moves through the space instead of assuming that the fans will automatically create uniform conditions. We can evaluate whether the airflow is reaching the crop zone. And the goal is to create consistent conditions across the crop zone without excessive air speeds or stagnant zones. One of the examples in the airflow we'll show is the placement of a mini air handling unit under two different architectural conditions. First, we look at it next to the wall, about 12 inches away, where the wall has actually helped guide the return plume upward and creates a more defined circulation path. And then we'll remove the wall and evaluate the same air handling unit in a more open condition to see how that unit is actually bypassing or short circuiting. Simulation is most valuable when project decisions are interconnected and costly to change later. It helps the team identify risk, compare options, and make better decisions before equipment is purchased and construction is locked in. Ceres can support the project at the level that makes sense for the current stage. That may mean answering one focused technical question, supporting early feasibility or concept development, or actually carrying the work through coordinated engineering. The level of engagement depends on how developed the project is, how complex decisions are, and how much support the team actually needs. Regardless of the engagement level, the outcome is information that project teams can count on and actually use for decisions and act upon. They may include climate findings, performance results, load profiles, CFD visualizations, design recommendations, coordinated engineering documents. The deliverables is not simply the analysis itself, it is a path forward supported by evidence. The earlier you involve the Ceres team, the more options the team has, and the less costly changes become. Early simulation will actually help identify risk and compare alternatives before the design is actually locked in. We can still actually help later, but fewer options will remain, and corrective changes are usually more disruptive and costly if they weren't caught up front. So with that being said, we're going to jump into IESVE. Let me change some screens real quick. And I hope the screen is sharing.
Yep.
This is the ISVE platform when you load it or launch it. There's some hot links that can take you to different locations, facts and questions, user guides, all kinds of good stuff in here. But we're just going to open a project for a demo here. Coming into it, it doesn't look all that special in reality. It's what you get out of it that's actually special. So these are two exact same size buildings. This one over here, let me move this out of the way. This one here is a fully empty building that's insulated metal panels, 3 inches all the way around everything. And then this is one of our standard greenhouses that we utilize, which has imps on the back, but all of this glazing up here is actually ETFE. One of the first things we'll do is a climate assessment for our client. So I'm going to try to pull this open here. I'm thinking, I hope the pop-up is showing. I'm not sure if it is or if it's not. But when the pop-up is here, we're able to go select where this location is going to be located, or where the project's located. Anywhere in the world, we do projects. And that's one of the reasons we like this software is we do a lot of work in Europe. We've done work in Saudi Arabia. We've done work in South America, North America, almost everywhere you can throw a dart for a greenhouse. We have done work there, and this allows us to do it efficiently. But once you actually pull in the weather data, just kind of take a step through this, what it looks like. You acquire the data like this, it pulls it in, and then now this is set for Boulder, Colorado. If I wanted to move this project somewhere else, it's easily to do that. And then we also go grab the simulation data, which will just select the nearest here, which is also in Boulder, which is already there. You can pull up and get it a couple different ways. But once we've got that in there and we saved, we can perform a climate assessment report by clicking this button right here. Instead of just making it run through the report and generate one, I did one earlier. It just takes a moment to do so. But I've got two of them to compare to show the differences. We've got one, which is the Denver International Airport, which is very close to where we're at here in Boulder. And this is a very useful document that will allow you to walk with your client through their location, see the design day for the mechanical design. And these are actually HTML at this point. So you can kind of come through here and change this. It's really nice to go get ideas of what's occurring at different points. This is a new feature ISVE has just recently added, I think, on this last version. And I think myself and my team use this very often to quickly understand conversations with clients when they're calling us. You have dry bulb information, wet bulb information, annual comfort hours, the monthly temperatures back and forth. You've got a psych chart for the area, annual humidity. But one of the main things that we use besides the solar paths here, sometimes for the PV generation, is these right here, these windrows diagrams. A lot of our clients come to us wanting natural ventilation buildings of one type or another. So pay particular attention to how these actually look. What this is the direction and the intensity of the wind coming towards the building at different times of the year. So this is Denver, Colorado, right here. Now, the interesting thing is I'm in Boulder as we speak, which is very close to Denver. And I'm just going to zoom down real quick to compare what that looked like, A versus B. As you can see here in Boulder, we get an absolute ton of westward forcing winds. We get 100-mile-an-hour winds quite often blowing through here at different seasons. And that is distinctively different than we were just looking at with the Denver, where a lot of it was coming from the south and maybe from the north. So this is one of the first tools we use. We actually can complimentary at most times provide a study like this for our client if they're calling in and needing questions and they're needing us to help guide them. We can pretty much do this pretty quick because it didn't take a lot except for entering their information and pulling it up and understanding their location. There's also, I'm going to talk briefly about Weather Shift. Weather Shift also has documents, aka files, that you can use to experiment with what you believe climate change may or may not be doing in the future. So we have done that on a few projects where you can kind of create intensities that you would not normally see in weather files. So that's a very helpful thing there. So now that we've discussed the climate assessment, we would assign the climate for the project. So now this is assigned to Boulder, Colorado, and then the project would then go through and assign the actual thermal construction. So this building here, as you can see, you can pick the floor, the ground, the walls, the doors, anything. And if you can't pick it, you can kind of go in and make it. So in here, we use the different types of glazing quite often. So we have ETFE glazing that we have constructed, single as well as this is just single layer here. But we also do double layer, triple layer ETFE. So I can come in here and actually create these families to then apply to the project. And then that allows us to put the correct properties with the correct building. Something else you can see in here, we'll talk about in two different ways, is a condensation risk and analysis. You can kind of come here and change values in here right now. At this particular set point that's in here, condensation will occur. You can change these values, and once you drop the dew point below the surface temperature, you'll get the ideas of where that property will condensate. So that's a helpful tool at times. We've got a lot of architects that ask questions about that. So once you go through and you have imported your geometry and you have now assigned the thermal properties to both buildings, you would then basically go through and build a thermal template of what is occurring in the building. I've got two of them here. I'm just kind of simulating cannabis and or tomato crops right now. I've got one set for greenhouse and I've got one set for indoor. And the biggest difference between the two of these are just the simple gains that I put in here. The gain is the actual load that's being removed eventually. So we have fluorescent lights and I have max plant transpiration. So as you can see, lights, I'm applying X amount of watts per square foot. And then under plant transpiration, applying X amount of latent gain without sensible gain per square foot. That is then tied to a schedule that would simulate how a plant would transpire. So whenever you put different things into this project, you then would go set how it would operate under a schedule, which is going to be down here. It's called AP Pro, and all of these are different schedules you can generate. There's a couple different versions of it. We're not going to go through how you do that, but that's how we're able to allow things to know when they're going to act or not act. Plants transpire more when the sun's out and it's a sunny day and they're getting water. And at nighttime, they do transpire some, but it drops down. So we apply the loads at the correct point in time of the day. There is suncast in here also, which you typically run ahead of time, which this allows you to understand how the sun is actually going to be performing on your building. Once that occurs, you can see the solar altitude, the azimuth, OK, TA, and direct normal radiation. So at this point, you can kind of see that what is hitting the building at what times and when and where and how. There's a lot of different types of analysis you can kind of go in here and do of looking at the KBTU hitting the side of the building. We like to look at how many hours of light we're going to get at different times of the year and things of that nature. So I'd say Suncast is helpful, but that's not the main place we live. Once we actually have the Suncast pulled in, you've kind of stamped it with the sunshine, so then you can kind of go on and rebuild the actual HVAC systems. You can build custom ones or you can kind of pull some in. I would never really pull them in because the custom ones always seem to be what we have to do for what we're doing. But once you make the HVAC system, this is one HVAC system for the insulated metal panel building, and this is one for the ETFE building. Systems are almost the same, except the fact that the actual coils and size of this nature are different. This coil is actually only 907 kBTU, and then this one over here is about 3993. But you go through and you can set and change the equipment to be what it's going to be. It's not just one and done. I mean, you kind of come in here and you adjust all of this. You then set control sequences to how it's going to actually operate. So every single component you put in has to have a control sequence tied to it of some kind to make it actually operate. And that process is done for both zones. So once you have your greenhouse pulled in, you have all of the assemblies identified, the properties done, you've pulled the weather, you've done all this kind of work, you can then actually start to run some analysis. The first thing you do is just run a loads test. This would give you a point in time. This is that one stamp in time of what that building's going to do. And then after you get that, you can start to go through simulations where we do every minute over 6-minute intervals because this is a greenhouse and it changes rapidly. If it's a different type of building, you could do that differently. But for myself, I find that that works actually really well. And instead of standing here and making you wait for the simulation to run, we're just going to look at some results because it's just going to be stand here for 5 minutes and see some things go across. I went ahead and pre-ran a few tests ahead of time. Once you get the test ran, you can come into here. This is called Vista Pro. Vista Pro is basically like the mind's eye to the building, is the easiest way that I can think about it, because almost everything you can think of in here is absolutely visible. So I've got a couple different versions I ran, and let me just go up here and see. Let's see, HVAC off, off and zero load. So I believe this first one here we're going to look at is both of these buildings with zero load and no HVAC turned on. So this is just if the building was sitting in that environment. There's two different color profiles here. One is the blue one is going to be the insulated metal panel air temperature, and then the red one is the ETFE chamber. As you can see, the ETFE, for some reason, obviously must be solar gain or something happening, has an absolute ton of energy in the building, and the other box is just kind of sitting there. It still gets warm, but there's not a lot happening in that building. We then go and we put the HVAC on. I'm sorry, we have the HVAC off, but we apply the actual building loads. So now you can see there's two different things occurring here. The actual insulated metal panel building looks a lot worse because it's a box, it's sealed and trapping all this in. We have LED lights in there creating heat. It cannot escape that box. And then down here, it looks better all of a sudden. Now, if we take and we turn the HVAC on to both buildings, we get a very uniform temperature for both. And this is kind of like what we typically are looking for. So instead of doing a full year, we'll just look at a day. And again, the red is the ETFE box, and the blue is the insulated metal panel box. So what we're looking at here is the air temperature changing and how the systems are operating, but they are both under control as expected. They just look differently because of how it's functioning. When this moment in time here occurs in the morning, we have usually the sun's coming up and or we're opening a shade cloth or a blackout curtain. That's now letting energy into the building. So it's dynamically different than a sealed box not doing anything at all. But let's go ahead and compare a few different things beyond that. We have the weather outside that we can go ahead and pull in here. If I can get to it. So the dry bulb temperature, we can get the dry bulb temperature that's outside at that moment in time. So green is now the outside temperature. And if we go to somewhere like in January, you can see it's much colder than the greenhouse and the insulated panel. And then during the hot summer, you can see that the outside temperature is far exceeding. The main driver for this is going to be the actual solar gain that you would see. So you can see in this building here, which is the ETFE building, we're getting a lot of solar gain getting into that building. And if you look at it over the full year, we have a lot of solar gain all year long. We use that heat quite often to heat, which is great in a cold environment, not so great in a hot environment. But even in January, we have a lot of solar gain. If we look at the other building, there's zero solar gain in that building because there's no windows to let it in. It's literally just a box made of insulated metal panels. So how does anything survive in that zone is by actually having light. So if we go in here for loads, we can go in here and look at lighting load. And then we can compare the lighting load between the two buildings. So building with the insulated metal panels is going to be very easy to understand because it's set to 12 on, 12 off cycle right now. So every day of the year, you're going to get the energy coming in and the energy on the whole time, and then it turns off. If we add in the other building, you can now see that this is absolutely different. It kind of kicks on for a minute, but then it turns off. And the reason it's turning off is we use PAR sensors in our greenhouses. You can simulate PAR sensors in IESVE, which then allows us to understand when to modulate the lighting. If we have full sun coming into this building, we do not need to use lights. The lights turn off. If it is maybe January, and we look at a time in January, you can see that every single day, it's just a little different than the day before. And some days it's on the whole day. Let's try to find, there you go. So there's probably a very shady day that day, lots of clouds, low sun angle. And when you compare that to the summertime, again, you just don't see that. But the other building at all times will have that pattern. So that building, no matter when you go anywhere, is still using the same light pattern. So that's kind of interesting. Well, this is great, you say. We don't have to use any light in a greenhouse. Well, no, you do need light, especially in wintertime. And if you want your crop to be producing correctly, you do want lights in there. It's not required, but we have them, and quite often we just modulate them and change intensities according to what we're seeing. Another thing that is very interesting is the solar load. So if we go down and we look for solar, which should be down here, solar. And if anybody from IESVE sees this, I would love to see bigger fonts on here. I have a hard time seeing this. So let me just type it in. Usually it pops up pretty quick, but I'm kind of, there we go, solar gain. So this is the main driving factor of the loads for this building over here. This solar gain, we've seen it a minute ago, is very high. Solar gain here, not at all. So when we're developing our buildings, we do have a lot of solar gain coming in. So it's not always the best. So what we actually do, and I can show you this in two different ways real quick. You can go in here and set, if you want to put shading cloth in. We quite often use energy blankets or shading cloths in our boxes. So if we go down here to thermal constructions and we go to the glazing, and we look at the roof. Earlier this morning, I went through and I turned on, you probably can't see it that great text-wise, but you can kind of come in here, and right here it says curtains, but you can kind of come in here and you can apply internal shade for curtains. You can do external shade. You can do local shade next to it. Quite often we'll have a tree or another building near a box that will need to actually mimic and show how that shade goes across. So we'll go in here and we'll turn on the shading. And then if we go back and we look at that solar profile again, because I've already ran that in earlier. Same building over here. We now have the shade curtain deployed. We'll go back to the solar. And then we'll just pick a nice sunny day here somewhere. So that's what the solar's looking like there. There. Comparative to the other. Same building. This is two tests we're looking at. Blue is without the shade cloth. I'm sorry. Blue is without the shade cloth. Red is with the shade cloth. So what this is allowing us to see is we put the properties in for the shade cloth. You've got to be cautious you put them in correctly. But once those properties are in there, you can then reduce your actual HVAC loads theoretically according to where you're at in the world, because our actual main load we battle is that solar load coming in. And I think that's very apparent that almost any and every day you're looking at here, we are getting a solar reduction in BTUs. Now, if we go to January, it's not as much always, but it's still occurring on most days. We are clipping the sun and preventing that energy from getting into the building. And then we do not have to remove the energy from the building if we prevent that from occurring. Another thing we discussed or said we would discuss is the condensation on products. So you can actually go in here as well and just look at the room and not have solar. And then you can still go grab dew point and air temperature. So there's air temperature. And then we want the dew point temperature of a pane of glass. So we'll go in here, we'll grab one pane of glass, and I want to see the surface temperature of that glass. And I've got something else showing still from a prior request. Oh no, it's showing it on both models. So let me just do the one here. And then we want to get the air temperature there. So this would allow you to see throughout the year when you're going to have condensation risk. Whenever you have your air temperature below that surface temperature is going to be an issue. Blue is the actual surface temperature of the glass. This is the air temperature in January, February, March. So you can see there's some points we get kind of close, and maybe we do condense a little bit right here on the 7th or 8th. Yeah, we'd actually have condensation right there. But to be able to come in and actually see and affect this with either A, controls, or B, hey, is the requirements to never have condensation. Now, in greenhouses and glass houses, quite often it's okay to have condensation, but it's really according to the client's requirements, because we can adapt and adjust that simply by changing the equipment, changing how it actually operates. There's lots of different ways we can kind of combat dripping buildings. Let's see what else we got here. Solar load, lighting loads, system loads and coils and fans. Another thing that's very useful is not just having the ability to go in and see surface temperatures of almost any property you see. We can look at the temperatures on the inside and outside of theoretically everything here. You can go get weather. Anything you want to see on weather is doable. But the more interesting part that we use quite often is looking at how the equipment itself is performing. So over here, you can select, like we're just looking at the zone, like we're doing right now. Or we can go ahead and we can do both HVAC systems. So here you can kind of come in and actually look at the coil, and you can see the total load that that coil has throughout the year. This is the cooling coil on the insulated metal panel for one day in April. And then if we pull this down over here, we can then go in and see the entire year. Now this sometimes looks noisy like this, but it is available in a format that you can then copy out and put into Excel. So if you're not happy using this tool right here, quite often we do pull out raw data. We'll put it into Excel and we'll do post-processing. But that way you can kind of get in here and see quite a bit of things. But if you look at this coil performance versus this coil performance is very interesting. Here's this coil here, and also the size of the coils. Let's pull this one back up. It's a little messy there. Same thing for the HVAC heating coils. You can see the sensible loads. And I guess real quick going back, I want to see the cooling coils late. I was trying to get to this. Total load, here's your sensible load, and then there's your latent load. So what's really nice is you can see the latent load versus the sensible load in here, and you can affect that with different types of equipment. So I use that quite often. You can also see the speed of the fan, the power that the fan's using, chilled water loops and lines. You can kind of go through and see the required cooling loads, things of that nature. So it doesn't matter what component you are attempting to look at, you have the ability to get in and look at it and make decisions based upon things that you are seeing and not just that one design day. I mean, this is not giving justice to the volume of things you can do in here. But at the end of the day, I would say this is probably one of the most powerful tools I have used to do an analysis on a building. I have used some of the other tools. I'm not going to name them by name. And I'm not saying that you cannot do some of these same simulations with those, but I do believe it may be more cumbersome for others. It was for me sometimes getting the geometry in there, getting things set up. And once you do the analysis for the heating and the thermal, we have the ability to go in here and do a lot of other things as well. We have macro flow, we have CFD analysis tools in here for CFD. There's egress, which I haven't used, but you could do egress, all kinds of cost and lifetime. And there's also a lighting program. We do lighting in here. The way we utilize it for lighting is we want to understand, I can show you this in a minute on another video. Let me do this. I knew I wouldn't have time to cover everything, so I figured I would do a real quick also compilation of some other things that Sean and Tyler had been working on and share this as well. So this is, you can see a model before we pull it into IESVE. This is a glass house attached to an actual house. That's the openings that we were identified. And then you can kind of see the air moving into the building and throughout the building, and you can move it around to actually understand how the air is moving once it gets into the building. Where is it leaving? How's it exiting? And that is where the windrows patterns really help us, because we can understand where this is occurring. We'll take all that information and we put it together into different types of reports that then will be material for the client to use to move forward or to not move forward on certain things. We also do retrofits at times. So we can, this is something Tyler did right here where he has modeled the actual grow benches with plants in them. And then you can kind of see the velocities going through as well as temperatures of that plant canopy. We stress these models pretty hard. And I think we actually push IESV to its limits sometimes. This is seeing the natural ventilation particle tracing inside of one of our greenhouses if we were just doing natural ventilation. This is particle tracing from an east to west, where you're just following the one particle. And this is the one which is kind of interesting. This is where a decision was actually made. This real quick right here. This was the actual pattern that we liked of what our HVAC system was doing because it was actually getting a really good mix against the glazing. The client requested that we remove the wall that was placed right behind here. And even though in our minds we were like, that is a terrible idea, we could then see how that air actually would flow. And then the last thing I'm going to show is kind of how we use this for lighting analysis. That was a building. And then when we go and we remove just that one far wall and made glazing on that far side like it was on the other side, we have a nice even map of it. And now you can kind of compare A versus B as kind of the things we're kind of looking at. So that in a nutshell is how Ceres utilizes IESVE for engineering projects and trying to understand and help designs. Consultants and architects and engineers work through projects. And that was all I prepared, Mary.
Thank you, Robert. That was incredibly comprehensive and very well done. We have quite a few questions. We'll see how many we can get through. If we don't get to your question, we'll try to follow up in an email, or if you have a question you want to email us, we'll put some contact information up on the screen at the end. A lot of these questions I think you sort of mentioned, touched on throughout the presentation. But we can just go one by one, and if they don't require lengthy responses, we'll just knock them out. So number one, someone asked, I know you're looking primarily at new construction, but can this be done on a retrofit rather than just on new construction? If someone wanted to take their existing greenhouse framework, assuming they had a solid existing structure with aging infrastructure, and needed to replace glazing and figure out how to optimize things like temperature, humidity, energy efficiency, light, need for artificial lighting, ventilation, etc., within the context of their existing framework, footprint, and site.
Yes. And I'm getting, hold on, for some reason, somebody's calling me in the middle of this. This should be happening. Okay. The answer is yes, and we do this all the time. Quite often, there's a lot of greenhouses that'll be brought in from other locations. And maybe they're from a European manufacturer and we've bought them here in the US. Somebody's bought it. We'll have clients call up and explain that it's not quite operating the way we want. So yes, we can go build a model of that greenhouse in that location and then give ideas of how to make it better. This is a very common thing. We will come out if necessary. We can do a site visit, come out, take pictures, understand the properties. Maybe you have the BOM of materials, the bill of materials of what actually was developed or designed. That's helpful. We can utilize that, pictures, videos. But the answer to that question is absolutely yes. Sooner the better, because your crops are not going to get better by doing nothing. They're just going to continue to be the same as they are.
Great. Next question is, how do you assess the economic trade-offs? Is there a way using the software? In the end, it's about return on net assets.
So that goes back to the OPR, Owner's Project Requirements. So every project that we get involved in, the first thing that we really focus in is what is the client asking us to do and how are they asking us to do it? And is this even possible or plausible? Most of the time it's yes, in one fashion or another, but capital costs can go up and budget constraints are an issue. So we have those very uncomfortable, comfortable conversations about what is the budget, what is your desires, and then sometimes we have to break some dreams and let people understand that what they're asking to be done for that price point is not doable. So they either have to lower the expectations to something that would maybe match what they can afford, or they have to have a budget high enough to build the product that they want. Because at the end of the day, you're building a system to grow something in it. You're making a custom box to grow, maybe it's tomatoes, maybe it's cucumbers, maybe it's a seed factory, maybe there's no seeds at all, maybe there's a bunch of humans going to be in a biophilic box for an event center. So there's different trade-offs, and that all goes back to the requirements of the project and what the owner wants, and very open conversations back and forth.
Great. Next, someone asked, they would just like to know how this software differs from the tools already used to simulate greenhouses and CEA microclimates. For example, and I don't know if you're supposed to say each letter, TRNSYS, ANSYS, Fluent as examples. Does it does it require a high performance computing platform to run, or could it be run on simple computers? For example, to predict the greenhouse response for 1 year, how much time will it take? Does it come with already established models and templates?
So it doesn't, so IESVE is not the only tool you can use to model. I'm just going to be clear on that. There are other tools out there. I have found it challenging to utilize other tools. And on those other tools, once you do the analysis for the loads and you can get the simulation done, it's really handy to have that model already ready to go for lighting as well as CFD analysis. So I'm not sure if all of those other software that's being referenced would do all of what's here. But for us, this tool kind of fits the bill. I have used quite a few other projects. On other projects, use different software, of which IESVE for me at this moment in time, I find to be the most efficient for our current workflow. So the type of computers utilized is typically it's a Windows-based system. This will not work on MacBook. I use a MacBook typically, and it will not work on it because of the actual architecture. So you have to put it onto Windows. It will not work on Parallels because it's 64-bit, and then Parallels tries to put it into 32-bit. So long as you're understanding that it will operate on a Windows machine fairly easily, not a problem. Processing time is according to what you're looking at, how dense your model is, how big it is, what all you're staring at, and then what's your stamp resolution? Like I'm doing it every 1 minute. Some people do it every 6 minutes, 10 minutes, an hour. It's according to your resolution that you find for your workflow.
Yeah, so along that same subject, someone asked if the software you've shown is publicly or commercially available, or is it customized?
It's commercial product, licensed by the year is what we do. We use three different licenses. We have three licenses here at Ceres. Myself, Tyler, and Sean both utilize it. And typically we're staring at the same and or different patterns of things, and we work together as a team.
Great. Any reason why you didn't use the spray component in Apache HVAC for adding direct moisture plus adiabatic cooling to the spaces?
Yes, because in that, we do that as well. We did not identify uh, plants in that fashion. We use plants as transpiration loads inside that we can tie loads to. You could probably do it both ways. For me, it's easier to put it inside of the actual thermal templates for the building. We use the spray chambers whenever we're simulating a fogging system or a wet wall.
Great. Do you use a typical meteorological year or do you average multiple years?
We use weather files, and it's just 1 year. And the weather files are typically best case of that zone. So a weather file typically isn't, a straight 1 year on. It's the most common things that are happening in that file is what we use. And they actually have, let me pull this up while you're talking quickly. IESVE has a space on their website to go get a bunch of different weather files from different companies. So I'm not going to go there. Just know you can go to their site and they'll direct you to paid as well as unpaid weather files you can utilize.
In the HVAC system, there is a heating coil, a cooling coil, fan, and a fourth equipment. What is it used for?
The fourth piece of equipment might have been seeing the filter in front of the coils, or it might have been the controllers at the far right end, or it could be a fan at the very bottom that was turned off that I use for exhausting. If we're doing a powered exhaust building, instead of going in and rebuilding everything at times, I can just take that same HVAC system, turn off all of these other components, and just use a bypass for air coming in the building and air going out of the building, and still see a performance in the IESVE's Vista Pro.
Great. Is it possible to model the evapotranspiration from crops?
Yes, and that's what we put into the template. So each crop has a certain amount of latent energy it's going to produce, basically per square foot, square meter of the crop. So what we'll do is we'll take whatever plant we're expecting. We'll do the research of what that transpiration looks like at different times of day if we're not familiar with the plant. And then we put the transpiration tied to a time-based distribution in that building because you can't just say, hey, here's 3,000 watts of moisture. Have a good day. It's got to be dispersed throughout the day because a plant, as it wakes up in the morning, it starts transpiring, has a peak time where it's creating most of the transpiration, and then it kind of, churns down towards the end of the day to a smaller trickle. So we do put that into the software, and yes, you can put that into the software. You just have to understand how to do it.
Okay. Are there any standard guidelines specifically for energy modeling of greenhouse buildings, like HVAC loads from ASHRAE or
Yeah.
CIB?
There's tons of things through AshRate that you can go get that explains this. We get into some very interesting buildings that are not typically uh, easily described in those um, manuals. So yes, we use AshRate quite often, but also sometimes the owner's project requirements has us veer away because the building is doing something phenomenally different than what we would normally see it do.
Okay. And what are the most common HVAC used for greenhouse buildings?
It's just according again to the location. I mean, we've got projects where we've used chillers, boilers. We've got our own DOAS systems that are DX. We are currently working on a project in Quebec where we're doing heat recovery with water to water heat recovery, where we're actually simulating all of the energy coming into the building. We're then capturing that, putting it into some buffer tanks, and then actually using it at the time, because there's a lot of reheat that would occur. So almost any kind of system that makes sense for the environment the project's going to be in. If you're in Canada at -30 and you're like, I don't want any gas bills, I want 100% renewable thought process, we can do a heat recovery facility. That's what we're doing now. So it's just according to the project's requirements again, Mary.
Great. I think that covers everything. Oh, wait, one more just came in. Do you use waste heat recovery?
Yes. And then I want to be clear on one thing, especially if IESVE ends up here in this project. We do a lot of storage with our projects. So the most recent one, I have to do a lot of post-processing because you can simulate on the cold side, having some cold storage. There's some limited heat storage on the hot side if you're doing a water loop. But I would love to see where you can actually have storage tanks that you can put in that ties to that heat waste recovery a little bit cleaner. It is not the most elegant for the heat waste recovery or for some of the recoveries, but it's coming along. They are giving quite a few updates recently that have some of that in it. So the answer is yes, but also it depends.
And did you model natural passive ventilation with the typical Ceres design?
Yes, we have. We've done passive as well as powered ventilation because we were very curious of how and where these buildings can work without a lot of electrical energy. So yes, we have modeled those and the results are different according to where it's located.
Great. Well, with that, I just want to close us out. Thanks again, Robert. That was really great, very informative. If anyone would like to reach us, we're available at info@ceresgs.com. If you're looking for more information specifically on this topic, at energy modeling, greenhouse simulation, we have a greenhouse performance guide we just put out there. If you visit our website, and the specific page is listed here, you can download the guide. It's free. Otherwise, follow us on social media. And if you have any questions, again, feel free to reach out. A recorded, this webinar is recorded and it will be sent to all participants in the next couple days. So just look out for that email. All right. I think that's everything we got. Thanks everyone for coming, and we'll see you next time.